So let's solve this one. You're going to be tempted probably to say, it's already factored. So I could say cotangent x equals 1 or cotangent x plus 3 equals 1, and that would be wrong, right? What you're attempting to apply is the zero product principle. But the thing about the zero product principle is that the product has to be 0, right? Not 1. It's not true that if this times that equals 1, that one of these things has to be 1. That's not true. This could be 1/2 and that could be 2. Their product would still be 1, right? In fact, there are infinitely many kinds of combinations that could work out so that their product is 1. So it's just not the case that one of these things has to equal 1. So what do we do? Well, when you were working on polynomial equations, what did you do? You expanded this, moved that over, and then refactored it, right? And that's what we're going to have to do here. So let's do it. If I distribute the cotangent, I'm going to get cotangent squared x plus 3 cotangent x equals 1. So thankfully that's not too terrible. Then we can move the 1 over. And now we can factor. Oh, and this one's going to be nasty, right? Because the only way to get a -1, right? The only way to get a -1 is to have like a +1 there and a -1 there. The only way to get a cotangent squared is to have a cotangent and a cotangent. But this isn't going to give you 3 cotangent x in the middle, right? This is going to give you cotangent squared minus cotangent plus cotangent cancel, and then -1. So this factorization isn't going to do the trick, and it's the only possibility. So, or at least it's the only possibility where we have whole numbers and all of that kind of nice stuff. So we can't factor it, at least not using normal, traditional methods. The other option would be to use the quadratic formula on it, right? So you think about this equation, it's quadratic in form. This is like u squared plus 3u minus 1 equals 0. So then you can use the quadratic formula. You can say, so then u equals -b plus or minus the square root of b squared minus 4 times a times c over 2a, right? Okay. Only, u is really cotangent x. So I'm gonna say, all right, so I'm gonna say cotangent x is -b plus or minus the square root of b squared minus 4 times a times c over 2a. Nasty, right? Holy schmoly. Well, let's see what we get. This is -3 plus or minus the square root of 9, looks like 9 plus 4. 9 plus 4 is 13 over 2. Okay. That is not pretty. That is an ugly, ugly answer. Well, that's okay. Sometimes you get ugly answers, right? So this is cotangent x. Now, we didn't have a rule that we listed out for cotangent. We only had rules for sine, cosine, and tangent. The good news is that it's easy enough to write this in terms of tangent, right? Cotangent is just 1 over tan. So I'm going to use the reciprocal identity there to say, all right, so tangent x is 2 over -3 plus or minus square root of 13. Okay, and that's all there is to that. The rest is pretty much history, right? We can say, well, it might be easier to write this out as 2 separate solutions, right? So I'm going to say plus or minus. Okay, I'm not going to bother with trying to rationalize this because we're not going to get an exact answer anyway. once we take tangent inverse, we're going to be dealing with decimal approximations in any case. So I'm going to say, all right, so then x is tangent inverse of 2 over negative 3 plus root 13 plus n pi, or x is tangent inverse of 2 over, oh, why did I make it 2? That should be a 3, right? So 2 over negative 3 minus root 13 plus n pi, plus n pi. So let's see about how much that is. I'm going to do tangent inverse 2 over negative 3 plus root 13. Bunch of parentheses there. That comes out to about 1.277. Same thing again, but with a negative 3 minus root 13. Okay, and I'm getting, for that one, I'm getting about negative 0.294. So if you're looking for all of your solutions, right, there they are, right? That's all of them. That's all infinitely many of them, okay? If you're looking for the solutions that live between 0 and 2 pi, let me do our little trick, right? If I plug in negative 1 for n, remember pi is about 3.14, so I'd be getting like 1.2 minus 3.1 or whatever. That's going to be less than 0, right? So I'm not going to plug in negative 1. If I plug in 0, though, I get 1.277. So that's in my solution set. If I plug in 1, then I'm going to still be, I'm going to be a little bit more than pi. So I'm definitely still within the interval. 1.277 plus pi is 4.419-ish. If I plug in 2 for n, now I'm bigger than 2 pi, right? So I stop. Same thing over here, right? If I plug in 0, I'm less than, I get an answer less than 0, so I'm not going to put that in my solution set. If I plug in 1, I'm going to have pi minus 0.294. It's about 2.848. If I plug in 2 for n, I'm going to have 2 pi minus a little bit, so it's still going to put me within this interval, right? So I'm going to have 2 pi minus 0.294. That's about 5.989. And then if I plug in 3, I'm going to have 3 pi minus just a little tiny bit. That's definitely going to be bigger than 2 pi, so that's where I stop. Okay, so there's my solution set for this problem.